And now, hello, hello, mic testing. Hi guys. You guys can hear me? Deva Goody and Gyara. Gyara Latif. Deva Goody. What's Deva Goody Tanishka? Latif? Guys, can you go unmute and confirm whether you can hear me? Can one of you do that? Students, can one of you unmute and respond to me whether you can hear me or not? Okay, thank you, Latif. So are other students joining? Is their lab over? No, it's confirmed by all students join the session. And start the session. Post your information. Okay. Have you guys joined from the lab? Can one of you respond? Boys and girls, can one of you respond? Yes, Pushpa, please go ahead. You have raised your hand. Hello, roll number 229X1A3314. You have raised your hand. Can you please speak? Okay, no problem. So are you guys ready? Or some more to join? All right. Then Vishnu says we can start. I was thinking, or rather, I thought Professor Suresh is going to confirm whether we can start, whether we have sufficient students. I think 50 students or 52 students, 51 students who has right now in the session. Do you think, do we need to wait for some more or we can start, is it? Is Professor Suresh in the session? We can start this session. Shall I start? Professor Suresh. Okay, I'm asking Professor Suresh. Okay. He's in the other class. So I understood you are in another class. Scheduled session. We have around how many students, guys? 51. We have 52. We have 50 students joined right now in this session. All right, guys, we'll get started then. All right, Let me close my WhatsApp, rather minimize. So, Vishnu, I'm starting, right? Okay, cool. I can't hear you, but I can hear only that bit where you said we can start. Excellent. So before we start, the concept or conceptual overview of the next algorithm, machine learning algorithm. So I'd like to say good morning to all of you. Trust you guys are doing excellent, and you started getting in the internal exam marks, and I trust all of you are getting good marks or grades. Having said that, I've changed a little bit of the program schedule, particularly on 3 aspects. I think 2 aspects maybe. Let me address one after the other. And then I spend a couple of minutes about the announcement for this week's project. And then we will dive deep into the session. So the changes are, given the feedback from students and also little logistical and administrative difficulties or challenges that we went through. So I thought that the announcement of the project will make it on each Saturday just before the session. The project for that session's topic, and the submission date would be not Sunday, but the next week, Wednesday. So there are 2 changes here. The announcement would come in on the same day as the session, each Saturday. 10 o'clock is what I've mentioned, which would essentially be released through the WhatsApp channel as well as in the Google Classroom. You might have seen today's announcement of the project, not at 10, but around 10:28 or 10:29 a.m. Submission date is not Sunday, but the next week, Wednesday, each week. Only the last week's assignment or project, which I believe would be the DTC decision tree classifier, you would not have much time. So you would have to present, or you would have to submit, complete and submit by Sunday. All of these changes are updated in the first course handout and uploaded to the respective session, respective unit, respective topic, which I believe is, I'm opening that. So I'm sure all of you would have seen this classroom, online classroom, classwork. So yeah, so here it's uploaded with those changes as a material. I'm opening this up so that you guys have clarity and know where to go to check. So as you can see here, announcement is 5th for this week's. I have highlighted. And then the submission date is 10th, which is Thursday. And this cycle continues for all topics. Announcement is 19th, session is 19th. Next week's is, I think, support vector machine. 12th is the announcement. Session is 12th. 13th, project detailed line by line code review. And 17th is the submission date. The same way it continues for the rest of the topics. So this is updated and uploaded and announced or published to the first course handout. So 2 parts are over. Third part, what was the third part? Yeah, this week's project. So let's go back. I don't know why I closed. Yeah, I didn't close. So this week's project announcement, week 4, project announcement, logistic regression, and then you can see the announcement PDF file, essentially the project description, problem statement, project title, description of the data set, description of the features, and then the source of this data and implementation steps. What are the files provided, timeline, etc., etc., yada, yada, yada. And the necessary data files, and then the watermark file as well. So that's the project announcement. All right, now with those announcements being done, let's jump into the session. I'll try to wrap it up in an hour. In case of any time challenges, let me know, guys, that you need to wrap up. You can't stay beyond 12 o'clock. And let me know, otherwise we may need another 10 to 15 minutes beyond 12 o'clock. All right.
Good morning, sir. Sorry to interrupt. This is Suresh.
Yes, Suresh. Good morning. This is Professor Suresh.
Yeah, please carry on with your whatever the schedule you have planned for today. Please carry on with that, sir. No issues right now.
Right. So do they have any class at 12:15 or 12 o'clock or 12:30?
12:20, they have lunch break, sir.
Okay, so we'll wrap it up by 12:15. Is that fine?
Fine. Fine, fine, sir. No problem, sir.
Okay.
Yeah, thank you, sir.
Thank you, Professor Suresh. All right, guys. So usual disclaimer. Agenda. So I have actually compiled this session deck, the content, and particularly for this session, particularly focusing on 360 degrees of the logistic regression. Usually you may not find this level of depth and breadth of the discourse on logistic regression in a single place. So I would highly recommend you guys pay attention and ask questions in case if you're not clear. Because some of the concepts that I would be covering here would be very useful, and they are the fundamental blocks, particularly the sigmoid function, logistic sigmoid function. They are fundamental, they would be fundamental, and they are fundamental blocks and concepts for advanced machine learning or deep learning algorithms, like as part of the neural network. The activation function essentially is a sort of sigmoid, a next level of sigmoid with the softmax, etc. So please pay attention to these concepts and even the metrics, model evaluation metrics, and then the receiver operating characteristics. What is it? You would keep hearing ROC. Many of the students and many of even those that I have worked with, my juniors and my team members, they do not know why is it called ROC and what are the key terms. These are super important for all of you guys. So pay attention. If you're not clear, ask the questions right away or send an email or WhatsApp message. All right. So we'll talk about, I'll walk you guys through the concept of logistic regression. Why do we need it when we've already learned the linear regression? And then what are the various components and aspects the logistic regression takes into account? How does it predict? It predicts based on probabilities. How are those probabilities derived or determined? And how are they related to the regression coefficients? Is there any regression again? Because there is a term regression in the name itself, logistic regression. How is it related to the regression? And what are the model evaluation metrics and ROC curve and the key terms? And of course, we spend 10 to 15 minutes on the project. What is the project? And this is actually a true challenge thrown by one of the companies. It's also available in Kaggle. And then what are the implementation steps? And some of the concepts for the implementation, which I would not be addressing now, but I would just show you a glimpse of which I would like you to go drill deep, dig deep, understand, and come back and ask questions, and definitely use those in your implementation for this project. All right, guys, I'm glad to see now we have 83 members present in this session. So this seems to be definitely a bigger session. So let's get going. So we have seen in linear regression last week, and many of you have submitted as well the project completing and predicting the Boston housing value, right? Value of a house, where we were able to predict a value, right? And what did we predict there? We predicted, the value of a house, 110,000 or 1,10,255, 5,236, 5,23,600, etc. In some cases, 3,25,656.25. So these values are essentially continuous values. It's essentially these values are on a value on a real line, which in this case starts from a minimum value, which is a bias value, or you can say 0, but bias is not 0, to positive infinite. That's a real line, it's called, right? So any value is any such discrete values are shown in a real line. This is infinite value and it starts with 0. This is called real line, real value line, right? And same case, if you take any other example where you apply the linear regression. For example, I have been talking about, for the electric two-wheelers, E2W means electric two-wheelers. They've been in the market for the past few years. So obviously, people want to sell the old one and buy a new one. So based on some data, if you are a company like Zip or any of these Royal Brothers, where you rent the vehicle, they might also sell these vehicles, and they have lots of data, so they can predict what is the used value, used electric two-wheeler value. So predicting that value, also a real line, maybe 1,05,235 rupees and 27 paisa. You're predicting it, right? So, or predicting a stock, equity stock value. These days, due to the war in between Israel and it's the conflict between all the Muslim nations and Israel, West Asia, it's called. You must have heard about the historical assault by Iran, 200 missiles being launched a few days back, I think Wednesday or Thursday, and then Israel receiving it. Fortunately, there was not much of the fatality, human fatality, but those events impact the stock prices, right? So what would be the stock, particularly those stocks that are related to, in a defense, or even the oil related, because oil is produced and we buy from those Asia, West Asia, right, Iran, etc. So how can we predicting those equity values or stock prices also is a linear regression. So in all these cases, what we are predicting is a target variable, is a response, is a continuous variable. That's what we call it mathematically. A value on this line, right? Any value, right? Here, it's a continuous value. Yes, Narasimha Reddy, you have a question? Go ahead. Sai Narasimha Reddy. I see you have raised your hand. Do you have a question? Okay, looks like it's my mistake, right? So these are all, these values are, this is a scalar, one value, and then these are continuous. But what if we want to predict or infer a target variable which is discrete, categorical? meaning some categories. There's also other discrete value called ordinal, order, right? First, second, third, right? If you are running, let's say IPL, so top eight, which one would be top eight? It's an ordinal value, starting with 1, 2, 3, right? And categorical is any category, right? Let's say, am I interested in buying? Are you interested in buying based on your past history of buying phones? Will you be buying iPhone 16 Pro which is launched just recently? Yes or no, right? Categorical discrete value. So how do we predict those categorical values which are discrete mathematically? Like a set, right? A set has a discrete values. Uh, of course, a set can have a continuous value with, I don't know if you know this convention. If a set has a continuous value, you represent that using 1 to 100. So this includes the values 1 and 100. And if it does not include 1 and 100, you show using brackets, braces, right? Curly or circular braces. So how do we predict those discrete values, categorical value, right? So predicting or inferring discrete values, let's start with a simple case of yes, no. Now we want to predict whether a user is interested in buying a vehicle insurance if he is already buying health insurance from a company called, let's say, ICICI Lombard, right? Because that essentially means if there is an interest, ICICI Lombard can spend more marketing effort to get more revenue or more policies, which will increase their top line revenue and also potentially bottom line profits, right? So let's take that case of simple case of only yes or no, or two categories, false or true, or interested, not interested, or success or failure, right? So if we take that case of two categorical values, one case being, I would like to buy a vehicle insurance if I am already a health insurance holder from your company, ICICI Lombard, then you can represent these yes or no, interested, not interested, using two values, 0 or 1. I'm interested, value 1. I'm not interested, value 0, which is a response. So that can be represented using a set. Y belongs to a set of two discrete values, 0 and 1, right? That's one example. The other cases, if you use credit card, and then there could be fraudulent transactions. So if you pick any random transaction out of, let's say, I've been using credit card since 1996 when I started working. Pretty much 90% of all my expenses, 95% are through my credit card. And it's possible that somebody might use it, and I have been traveling across the globe and they have my credit card data, and I have been running lots of online purchases, not only from India, but those from US as well, Europe as well. So they have access, and that data can be leaked or kind of hacked by hackers, and they could use my credit card for the transaction. So if I pick any transaction, is that transaction fraudulent or genuine? Again, 0 or 1. So that's the other example, right? And let's say if a person has been having lots of stomach problems for the past so many months, and there have been fever continuously, and there has been no respite even after lots of clinical therapy. So the person may go for, there is a suspicion, and then he may go for some MRI, CT scan, and all that to suspect if there is any malignancy, cancer causing, if there is any cancer causing things in his body, in his anatomy, right? Tumors, right? So you get the radiology report, and we can feed that radiology report and see whether is there any malignancy, is the disease, is the malignant tumor present or not. This is being used across the globe because it's more deterministic and definitive than a human looking at it. So far, it's been done before the computers. It was an expert doctor who would visually see those radiology scans and then decide visually based on how visually the area, scanned area looks like. Can be he or she can detect whether it's a malignancy or benign tumor, right? So there are many such cases where a binary discrete responses are expected to predict based on lots of input data. A model can be built, and that would help us save time and bring efficiency. Right? There are also cases of multiple possible outcomes. For example, let's take the same case. You already have a phone from Oppo, but you may be interested. Google Pixel has released a new phone recently. Samsung Galaxy Ultra or something, I think Galaxy Note Ultra was released recently. So you have 4 to 5 options. Which one would you choose, or which one would you buy if we have lots of data about people like you in the past? So there are multiple options, categories, discrete value, out of which one needs to be predicted. And these days, the chat GPTs and the DALLs of the world, you feed in an image and it can identify whether this image is a cat, dog, bird, car, bus. So various categories, various possible options. So that's a multi outcome or multiple responses out of which only one needs to be selected. So can linear regression, which we have learned and studied and did a project last week, can it help us predict or apply or to be leveraged for these cases that we just talked about? Turns out it is not, because the linear regression is predicting continuous values which are unbounded. There's no limit, right? I mean, it starts from anywhere from 0 to infinity, though it may not be infinite value, but it's a finite value, but it's a huge number. So it's unbounded, and it's definitely not between 0 and 1. But if you take the case of a binary classification or the binary responses, right? Yes or no, true or false. Hence, linear regression is not suitable, right? So we need a model that would provide us discrete values, binary classification, or multiple value classification, also called multinomial classification, right? Multinomial classification. So outcomes are not between 0 and 1, at least for the binary classification when we use linear regression, and it's unbounded, right? So we need a model or a mechanism or a technique that can map a real valued regression value, just like the linear regression that generates a value, but that value needs to be mapped to the one of the known outcomes, either 0 or 1 if it is a binary classification, or multinomial classification. It has to map to one of them. So if it is mapping to one of them, it would be some value between 0 and 1. You will learn this as a softmax later on, where it essentially means it's the probability, right? So we need a technique or a model on top of the regression, where regressors collectively, based on the linear transformation, will give you a real value which needs to be transformed into a value either 0 or 1 or between 0 and 1. If it is 0 or 1, this is a hard value, so also called hard classification. If it is between 0 and 1, any value between 0 and 1, which is nothing but a probability, it's called soft classification, right? So essentially, the logistic regression is nothing but taking a linear regression and then transforming that using some sort of logistic function, which would transform that real value either to 0 or 1 or between 0 and 1, as you can see here, right? As you can see. So till this point, it is nothing but your linear regression, right? You have your regressors, feature values, 1 to n, x1 to xn, which is nothing but vector x, input vector, feature vector x. You guys can hear me clearly, right? Students? Can somebody say or type some? You can hear me? Thank you, Vishnu. Right. So this is a feature vector, right? And then a linear transformation, nothing but a value, a weight, multiplying the feature vector, or rather each feature. Jeevan, Hanumalapati Jeevan, do you have any question? You have raised your hand. Please go ahead if you have question. Okay, I think you lowered your hand. Okay, so let's go back. So this is nothing but your linear regression or linear transformation. Nothing but each value, feature value, is multiplied by a weight. Earlier in the last class, I used H0 or HI, but here I'm using W. Doesn't matter. Globally, the convention in the academia and as well as in the industry for the mathematical expression for the weights, either W or H. H is more used in the academia, W is used more in the business side, company, enterprises side, or the product side, right? So this is nothing but a linear transformation. It's multiplying each vector component or each feature with a weight and summing them up, right? So, and then transforming that real value into either 0 or 1 or between 0 and 1 using a function which is called logistic function, or also called sigmoid function, 1 by 1 plus e to the power e raised to the power minus z. And what is minus z? Minus z is nothing but our linear transformation. Weights multiplied by input vector. The linearly transformed value, the input feature vector multiplied with the weights vector or regressor coefficients vector, and all of them summed up. So this is the sigmoid function which will produce a value between 0 and 1, also called logistic function. Hence this model, and this produces between 0 and 1, or 0 and 1, or between 0 and 1. Again, we can tweak this around to produce 0 or 1 or between 0 and 1. Hence this model is called logistic regression. So as you can see here, if we add some filtering, if the value is greater than 0.5, just like rounding off, all of us know rounding off. If you have a decimal value 0.9, if you want to round it to the nearest integer, and usual conventional logic is anything above 0.5 is rounded to the nearest nearest integer, in this case 1, and anything less than 0.5 is rounded off to the nearest lower integer. It's also called ceiling, right? There's a mathematical ceiling function as well. All of these, pay attention, you would need to understand and remember. All of these are used in AI ML implementations. So it's here, we either upper seal it or lower seal it. That's the rounding. And obviously, since it is the sigmoid function is producing output based on the regressed value, integer value, real value between 0 and 1. You can think like it's a dancing S curve. It's also called S curve because the lower value is 0, upper value is, or maximum value is 1, also called S curve, right? And it's smooth, right? It's very smooth function. Smooth in the context of differentiability. If a curve, if a function is, let's say, straight line like this or straight line like this, the slope of these curves is either 0 or infinite, which means the first derivative of this curve or these lines is 0 or infinite. So they are not, it's tough to, I mean, there's no differentiability. 0 is no differentiability, infinite is beyond differentiability. Why differentiability? Because we remember we talked about finding the optimized values using, gradient descent or gradient ascent, global local minima maxima, using the rate of change and then applying that to 0. We need the derivative or the differentiability. So this is a smooth curve, hence it is differentiable, hence it is easier to find the minima maxima, potentially minimum value, right? A little bit of little teasing questions here, but we've also talked about the logistic regression being used either for binary classification or binary prediction, or multiple valued prediction, which is known as multinomial logistic regression. Multinomial logistic regression. We also talked about it, where the predicted value is one among more than two values, but a finite set of discrete values. All of these are discrete values, right? Essentially, the predicted value in the case of logistic regression, either 0 or 1 or between 0 and 1, they are nothing but the probability of what you are predicting or the discrete outputs or discrete predicted values and their probability of being occurred for that particular input instance that you are trying to predict. So net, what it means, what rather logistic regression is predicting is nothing but the probabilities. So in case of binary classification, it's predicting 0 or 1, right? So what is the meaning of 0 in probability? Probability of an event occurring 0 means it won't occur. That means that particular class is not predicted. Whereas probability of an event occurring is 1, meaning it is highly definitive, which means it is occurring without any doubt. So it is predictable, predictive. That means if it is 1, this is what I am predicting. If S is 1, and if you found output after your linear regression, logistic regression sigmoid value is 1, that means yes is the response, 1 is the response, whichever category of mapped 1 to. Usually you map 1 to yes, true, success, 0 to fail, false, no, etc. Right? We'll be focusing on binary logistic regression algorithm in this project and in this session and in this course or in this program as well. But the multinomial classification essentially as a classification rather than predicting 1 out of multiple. That's also possible, but usually the deep neural networks are used. But classification as a classifying into multiple classes of any input data, we would be spending a lot of time on multiple algorithms like SVM, support vector machines, and then decision tree classifiers, and then I think there are a couple more, right? So we've talked about the, let's go back, let me clear, right? So here, this is the sigmoid function. Now I'm going to ask you guys, one of you, what would be the values for certain boundary conditions or certain cases? If the z value, the regression linear transformation value is minus infinity, what would be the, I think this is not correct, this should have been just sigma z. So if z value here is minus infinity, what would be the value of sigma z? Sigma z is the classical representation of a sigmoid function. Sigma, this is a Greek alphabet sigma, smaller sigma. Bigger sigma, as you know, is for the summation, right? So what would be the sigma z value if z equals to minus infinity? Anyone? Absolutely, Vishnu. It is 0. Because how it is 0? Let's just derive this 1 by 1 plus. Do you want to explain how it is 0? Vishnu?
Sir, by substituting minus infinity, we get 1 by 1 plus
1 by 1 plus e to the power
infinity, sir.
minus and
Minus of
minus.
minus infinity.
Okay. Now, minus of minus is plus. So this reduces to 1 by 1 plus e to the power infinity. As we know, e is, the exponent, right? The reverse of ln, natural logarithm. So e to the power infinity is infinity. 1 by 1 plus infinity is 1 by, this is equivalent of, let me put this, 1 by 1 plus infinity. And this is equivalent of 1 by infinity. Infinity plus 1 is infinity. Infinity is nothing but something beyond what we can comprehend or count. We meaning we as humans, right? So it's a convention, right? If numbering itself is a convention, humans have, invented or created for the convenience over the thousands of years. Right? So 1 by infinity, when you divide something beyond countability, such a huge number, when you divide 1 with that, naturally the division, the parts would be pretty much tending to be 0. Hence it is 0, right? Now let's ask the other. So if z equals to infinity, what would be the alpha z value? Anyone? When z equals to just infinity, positive infinity. Anyone other than Vishnu? All right. Syed Suleiman, can you unmute and share your explanation how and why it's 1? Syed Suleiman? Anyone? Okay, Somara Geetika, can you speak how it is 1? Can you unmute and speak? Deepika? Somara, Deepika, right? Geetika, sorry. Geetika, can you unmute and speak how it is 1? Okay. Anyways, let's We don't have much time. Okay, 1 by 1 plus, let's derive the same way. E to the power minus infinity equals to 1 by 1 plus. What is e to the power of minus infinity? 0. How? Let's put this here. E to the power minus infinity equals to 1 by e to the power infinity equals to 1 by e to the power infinity equals to 0. Oh, what happened? Right? So 1 by 1 plus 0 equals to 1 by 1 equals to 1. You're absolutely right, all of you. Right? So when alpha is 0, sorry, z is 0, when z equals to 0, what is the, not alpha, sigma? Absolutely. Sigma z is 0.5. How 0.5? 1 by 1 plus e to the power minus 0 equals to 1 by 1 plus e to the power minus 0 is nothing but e to the power 0. E to the power 0 is nothing but, as you know, algebra, anything raised to the exponent value 0 is nothing but 1. So 1 by 1 plus 1 is 1 by 2. 1 by 2 is 0.5. That is a midpoint between 0 and 1. Right? So these are all important mathematics computations, particularly sigmoid function has to be part of your life going forward as an engineer. If you are going to build AI ML or computing career, particularly in the machine learning and then the AI, sigmoid function is going to be there with you all the way as long as you are there. So better get to grips with it, understand the complexities and the nuances of those, right? Taking a lot of time already, let's go quickly. So if you plot the graph, particularly for these three values that we just computed, and this would be the graph, right? So when it is minus infinity, it is 0. When it is 0, it is 0.5, and when it is infinity, 1. Just a second. Just a second, guys. There's something urgent. All right, sorry, guys. So I hope you can hear me. So we've derived the value for all of these. What happened? Okay. Okay, so this is the, when z is 0, which is 0.5 value, and this is 1 when it is positive infinite, when the z value is infinite, when it is minus infinite, right? Both are there here already. So this is a sigmoid function. So essentially, it's a smooth function, differentiable, and it's also called activation function in neural networks. And this is the last piece of a neuron. In fact, this is nothing but your neuron, right? One neuron or perceptron, and multiple of such neurons or perceptrons would exist in one layer, and you would have hundreds and thousands of such layers in any deep neural network, and be it in a simple ANN, or be it in the transformers, be it in any deep learning models. You would have hundreds to thousands of layers, each layer comprising of hundreds to thousands of neurons. So pay attention, understand these very clearly. This is a simple linear transformation or linear combination with input values and some weights. That is nothing but your guess. Even when we talked about what is the value of a plot if you are trying to buy next to the polarity college, there are 4 or 5 factors. How far is it from the main road, and then whether it's north facing, east facing. These are all the features. And which one will you value more? Maybe how near to the road, then that has a higher weightage. And then you add them up and you essentially transform that into between known values. So this is the core of any machine learning, be it normal learning, be it deep learning, be it neural network based learning, right? So get these fundamentals very, very clearly. It's nothing but a neuron, right? So we looked at it, we looked at this. Now let's now try to address, so what is being predicted we understood as probability or probabilities, right? So let's try to look at the mathematics behind it and try to put a mathematical model / representation for the outcomes of the logistic regression in a very simplistic terms, not complex at all. We already know input, which has multiple features, can be represented, it's not a scalar, can be represented as a vector, and it has n features. And what is the one on the top here? Anybody can respond or type? What is the one doing here? We know x1 to xn are features. What is this one? You guys can hear me? What is this one? So one is nothing but, yeah, I see that you can hear me. It's nothing but your bias, right? So we said we will represent for the convenience, mathematical computational convenience. We consider the bias also as a vector input feature, but has a value 1. So the weight of the bias is a true bias. This is only for the convenience. We've talked about it in the linear regression. So this is our input vector. Now, and this is important, so pay attention here. So probability of output, this is output variable in case of binary classification or binary prediction, binary output prediction. Probability of output predicted value being 1, true, yes, interested, all these values can be mapped to 2, given input vector x bar with values, right, is represented is equals to sigmoid function 1 by 1 plus, and what is this? Instead of z, we are seeing this x bar transpose w, that is nothing but your linear transformed value, regressed value, right? Weights multiplied by your identified weights till that point, and the features or feature values for that particular data point or data observed data point. So the linearly transformed value of feature values and the weights vector, that value as an exponent minus of that minus of that as an exponent, e raised to that exponent, is the predicted value being success or 1 or true, right? And usually this is represented as gx, a success, interest, then yes, or represented probability of output being prediction being 1 given any input vector x bar or feature vector x bar is represented as gx, right? Now if I want to know from basic probability, I want to predict probability of output being 0 given input feature vector x bar. How can I derive this value without computing using any formula? Anyone type or speak? If I know probability of success or 1 is some value, what is the probability of failure? Anyone? One minus p. Absolutely. So that is what we see here. Probability of y being 0 given input feature vector x bar is 1 minus probability of y being 1. So if you obviously substitute the probability of being y being 1 given x bar feature vector, so that's you would essentially get this value. That's nothing but 1 minus gx. Again, these derivations are super important. These are the basic fundamental derivations, just like our division and multiplication and then the addition arithmetics in machine learning. So please understand them and ask any questions if you are not clear. And what are these vectors? These x, w, etc. We talked about y being the response value, right? Let me check. Y is the response or target value. X bar is the input feature vector. W is the weights of the feature vector that we have derived based on gradient descent or gradient ascent, whatever that is, right? So how do we determine the next equation, these regression coefficients, which are the W vector, right? So logistic regression uses maximum likelihood estimate. Again, this is a fundamental concept, maximum likelihood in statistics and in signal processing, and it is a core concept for machine learning and AI. So if you are not clear, please take a deep dive into it, understand it. It's nothing but simply estimating, again related to the probability, what is the likelihood of certain event occurring amongst multiple events, nothing but a joint probability. So it is nothing but probability of more than one event collectively occurring. Again, it's a combination of probability and permutations and combinations. If let's say in IPL next year, out of 10 teams competing, how many teams would be in the top 8? There are loads of combinations. How many combinations? 10 choose, rather, yeah, 10 choose 8. If there are 10 teams, if we are expecting how many 8 would be the top teams, it's a 10 choose 8, 10C8, right? So what is the probability among these 10C8, a particular order, let's say Sunrisers, SRH being on top, number 1, number 2 being the Bangalore team, number 3 being Mumbai team, only one combination, 1 divided by 10 choose 8, that is the likelihood probability. And how can you maximize that likelihood, right? It's a gradient ascent. So we want to maximize rather than descent is for the minima, ascent is for the maxima. Again, these are the basic calculus that you must have learned: local minima, local maxima, global minima, global maxima in your 11th or 12th or maybe first year M1 or M2 differential calculus, right? Limit theorem, etc., limits, etc., right? So maximum likelihood for a given combination using the gradient ascent is what is used to compute, to derive iteratively. This is done for each training sample that you have iteratively, also called online learning algorithm, is what is used for determining the regression coefficients. So as you can see, any next coefficient vector value, it's a vector, is based on, you start with some random value, and then that value plus some step or learning rate. In fact, I've derived it here because of the lack of the time. I'm not going to go into it. You can take a look at it and ask questions tomorrow. I will be publishing this deck, right? Any step function, and then the current response value because you are training, and then the predicted response value based on the sigmoid function. And the difference of these is nothing but error in prediction. And how do you predict it? Based on the vector of your coefficients that you have derived in the previous iteration, previous data sample, and multiply that with the current feature vector value. K is the instance number of your training sample, right? So I have also explained. So the update value, and that's how you would derive it your update. You would derive it. You derive your update regression coefficient vector value. So current estimate, step or learning rate, right? And then your predicted value, your actual value, your predicted value. Collectively, the difference is your error, prediction error. Obviously, we want it 0. So when it is 0, which means we have converged, and you don't need to run any further iteration in the training to determine the regression coefficient vector, right? And it takes a lot of iterations. So now we'll get into we'll address how do we evaluate the model metrics. There are 4 to 5 parameters. Metrics essentially to see the efficiency of the model. So accuracy, and there is a new accuracy, you all know, essentially how many out of, if you have predicted 100 out of 100, this is the training accuracy. How many were the actual true predictions? Maybe 98 out of 100, 98 were the right predictions, 2 were the wrong predictions. So then your accuracy is how much? What percentage? Out of 100 predictions, 98 were the right predictions, 2 were the wrong predictions. What is your accuracy? Anyone? 98%, obviously. Absolutely. Correct, Vishnu. So that's the accuracy. Accuracy also, I'm going to not talk about this particular, just a second, this particular point here, right? Where is this particular point? Imbalanced data set. I'm going to address this tomorrow because this is very, very important, and our project is an example of imbalanced data set. So we will talk about it tomorrow. And then there's a second factor called confusion matrix. Okay. What is confusion matrix? Let's address confusion. What is the meaning of confusion? We are not clear. And what's we not clear? Potentially in the context of regression, logistic regression, we're not clear whether the prediction is right or wrong. So we are confused about the prediction. Not when we say we, our model. So is our model confused because it is predicting wrong values right and right values wrong? Or it is predicting positives as negatives, negatives as positives? Or it is predicting zeros as 1 and ones as zeros? Or it is predicting true value positive as a negative value, which in English called false negative. False negative meaning it is actually not a negative. It is not no, but it is predicted as no. So hence it is a false negative. So confusion matrix is nothing but, since you have 2 parameters to predict and there are 4, you can do 4 combinations, right? 2 out of 2 is 4. You can make 4 combinations. So there are 4 combinational confusion matrix values. These are like a matrix, and hence it is called a confusion matrix. So let's understand a minute. So This is our predicted access. This is our actual access. Let's say actual value is positive. Now, we have predicted that as positive, which means it is the right prediction. It is the true prediction. It is the true positive. Correct? Now, actual value is positive, 1, but we have predicted as 0 or as negative. But actually, it is not negative. So, it is a false negative. It is actually positive. Hence, it is a positive false negative. Let's take actual value outcome was negative. Our prediction, our model predicted that as positive. Actually, it is negative, but it's predicted as positive. But it is actually not positive. Hence, it is false positive. Now, let's say actual value is negative, but we have predicted as negative. Actually, it is negative, which means false, 0, not interested outcomes. And we have also predicted that as negative. So it is a true negative. So this matrix, these values are nothing but when organized like a matrix, like here, it's called confusion matrix. And this is a measure of how each model is performing for the prediction. Any questions, guys? This is very, very important to understand the confusion matrix to evaluate the efficiency of the prediction. Any questions, guys? Feel free to ask a question if you have any. None? Okay, let's go to the next. There's also another metric or another term which comprises of a bunch of metrics that are used in evaluating the performance of this model, logistic regression, called receiver operating characteristic curve. So essentially plotting various values at various operating levels. So you may get confused. Why are we talking about a receiver when we are talking about a prediction algorithm or a model, right? And where is this coming from? Where does this emanate from, right? So this has roots in the signal processing and statistics. As you know, entire AI and ML is an offshoot, is born out of wireless communication or communication engineering and statistics. The genesis comes from there. That's the reason you see many of these models and information theorem, entropy, all these, the basic concepts are invented and created by pretty much all communication, telecommunication scientists like Shannon, all these guys, right? Claude Shannon. In fact, the Claude AI machine, AI application that you might have seen, Perplexity's Cloud, is named after Claude Shannon. Shannon is the guy who invented the sampling theorem and then this information entropy and all this, right? So these term, the term receiver comes from signal processing, communication engineering, and statistics. So this used to represent essentially to detect a signal out of noise. You know, when a signal is transmitted over either a wireless medium or wired medium, it gets disturbed, right? It gets adulterated, it gets perturbed. And at the end, whether it's your mobile phone or whether it's your telephone, landline phone, you need to have a clearly isolated signal, the voice signal, from the noise so that you can have a distinct, clear conversation and communicate and have a dialogue, right? That's how the receiver operating characteristic to identify the signal from the noise got originated. The same way, that signal is nothing but either 1 or rather 1 out of 1 or 0 for our output prediction, right? And this also essentially was used principally in the radar communication, radio. uh, I hope all of you know what is the abbreviation or the expansion of radar. Radar, radio. What is that? Radio? Anyway, I'll leave that to you guys. It's something with ranging, right? Maybe one of you can tell me tomorrow what is the expansion of radar. So radar was used to identify border flights, during the war or to protect the border. And if any vehicle is, particularly the aircraft is passing through, whether it could be a simple big bird or anything moving. So we need to identify whether it's an aircraft or it is not an aircraft. So is an aircraft is a signal, not an aircraft is a noise, right? So that's how the ROC was originated, created, or the receiver operating characteristics or the curve. And then the logistic regression also trying to do the similar thing, to distinguish signal from the noise, 1 from the 0. So for creating a model, creating a curve of this under various conditions of noise, various conditions of inputs, is the curve that would also help us get the characteristic, operating characteristic of the model. So it's a plot where it plots the false positive rate. It's nothing but true positives and false positives. True positive rate is called recall. False positive, also it's called specificity. And false positive rate, essentially what is the rate at which the falses are occurring, right? So true positives, false negatives, true negatives, false negatives, we've looked at, we understood in the confusion matrix, right? I'm going to skip that. What is true positive rate is nothing but, let's look at these 4. Out of all actual positives, now we are here, out of all actual positives, how many the model correctly predicted as positives? So it includes false negatives and true positives is essentially what our model has predicted. That number needs to divide the true positives. So that is a true positive rate, also called recall, also called sensitivity. How sensitive it is, how sensitive it is to the true prediction or true prediction, or its prediction being true. That is the sensitivity. False positive rate, essentially it is insensitive in a way, right? It's predicting false things also as a positive things, right? So how many actual negatives are incorrectly identified as positive? So that's a false positive rate. There's nothing but your actual false positives divided by false positives and the true negatives. True negatives also are the false positives, right? In a way, positives, right? So that is the FPR. Then specificity, how specific is the model's prediction is. Out of all actual negatives, how many it has identified the true negative, how many true negatives it has identified. So true negatives plus false positive. False positive also is a negative. So if the false positive is 0, that means our model is 1. Perfect. When it comes to the specificity. The same way, if false negatives are 0, that means true positives are 100%. That means it's the best. So we want sensitivity being 100% 1 and specificity being 1. E model with the same weights, it should give sensitivity and specificity being 1 and 1. That is where we would like the receiver to be operating. So if you plot them as a 2-dimensional curve, obviously the area under this curve would be 1. It's also called AUC, area under curve. That is nothing but the next one. But it is it's almost impossible to get AUC1 because there would be some error, even if 99.99%. So it will not be 1, right? So there is also F1 score. Probably I'm going to skip these because we'll spend more time tomorrow interpreting this tomorrow, in the project. So I'm going to quickly skip these points and then spend another 5 to 10 minutes in the project and displaying the outputs of the project so that you get an idea. Right, guys? You're fine with it? Or any questions, guys? We'll wrap it up in next 5 to 10 minutes. I know you must be hungry. All right, I'm sitting in between you and your lunch, as I understand. So project it's announced. You can go read through the announcement, but I'm going to quickly give you an overview. So there are around 100,000, around 3 lakh users who have bought a health insurance from a company X, say ICICI Lombard. ICICI Lombard also offers vehicle insurance, and vehicle insurance is mandatory. Without vehicle insurance, you can't register your vehicle, and then vehicle insurance is annual, so you have to renew each year. So some part of the vehicle insurance can be bought for 2 to 3 years. It's called, I think, own damage or third party damage. One of them you can buy for 2, 3 years or 4 years, but the other you have to keep buying each year, renewing each year, right? So ICICI Lombard wants to know, among its 3 lakh existing healthcare insurance customers, it wants to know how many of them would be interested in buying if they start a new business for vehicle insurance, because it's a business, it's for profit. But before investing into marketing effort and establishing the business, they want to get a sense of how many would be interested, because they already have a data. And if somebody can tell them, build a model and give them a look, there are lots interested, 30% interested or only 1% interested, then ICICI Lombard can accordingly make an investment into this business or may not make an investment into this business. And hence, this project is asking you guys to build a model to guide and advise ICICI Lombard in giving a definitive quantified sense of the interest of the users, existing customers, also called incumbent customers, that would be interested in buying vehicle insurance. So that's the project. And what would you generate for this? You would generate, obviously, whether they are interested in buying or not, 1 or 0 value for each customer in the test data set. But the existing customers, they have also done some survey, huge survey, and they have given a data of existing customers who are interested, around 1 lakh change or 2 lakh change, who are interested in buying the insurance for around 1 to 2 lakhs, and they have given another 1 lakh to predict whether they would be interested or not. Right? So there are 2 sets, train.csv and test.csv. Right? So, and then of course I have given also one more image, and then which is for plotting, using as a watermark for the plots. And the last one is obviously the shell code IPyNB file, Jupyter file. Right? You have to build a model. These are the features. What are the features it has? The columns: unique ID of the customer, the gender of the customer, age of the customer, whether the customer has a driving license, which region are they from. Most of them are the continuous values. Some of them are categorical values. There are no ordinal values here. I think there are also ordinal values, right? Like vehicle age, above 1 or below 1 or something like that. Vehicle age must be a continuous value. No, I think it could be, yeah, it's a continuous value. Vehicle damage is the categorical value, so there are no ordinal values here. Annual premium, how much the customer needs to pay for the vehicle insurance each year, and then what are the channels that he was reached out when the training data was collected. Channels as in whether over the phone, telemarketing, email, in person, or through third-party agents, right? TPA. Vintage is how long the customer has been with the ICICI Lombard as a health insurance agent, a customer. The response we want you to predict, I want you to predict is whether one, interested to buy in vehicle insurance, also called here, it's called cross-selling because you have a customer buying something from you and you are trying to sell across some other product. Hence, it's called cross-sell. It's a standard marketing term called cross-selling. And that's what many companies do. If you have and that's what creates a lot of value to existing companies because you are selling something and you can build something else and sell related something else you can build and sell to the customer. Then your marketing expenses are minimal because you're not trying to get a new customer. You're trying to get an existing customer. The marketing expenses are always lesser. Right? Data sets I talked about. So the training is around 381 rows. In the test, 127. So the data collected based on the forms, whether they are interested or not, is 381,000. And company wants you to predict for 127 whether they would be interested or not. Features are 10. Response variable is 1 or 0. Which are the features? Some of them are categorical, some of them are continuous, right? This data is available on Kaggle. You can download them from the Kaggle. And this is essentially a sort of challenge thrown open by one of the entities. You can find that data and that guy's name, I think you can find in the link, right? And submit it by Thursday and then implementation steps. So I'm gonna skip, I have not talked about, this particular 2-3 options here. I'm leaving them open for you guys to figure out. I'll address them tomorrow in the session, right? Yeah, I'm gonna skip these and I'm gonna show you guys the output. Right. Just a second. So let us move this out and let's look at the code. Right. So, all right. So all these, so this is to a function to add the watermark and loading the database. I'm highlighting, I hope you guys can see. And then check for any missing values. Somebody raised a hand. You guys have a question? Okay, so slow ahead. And then this is for encoding the categorical values, gender, vehicle age, vehicle damage, and then for the training purposes, separating the input and the output labels and then the feature values, splitting into training, 20%, 80% training, 20% prediction in the training to build a model. I'm going to skip this. You guys figure it out, and if not, tomorrow I'll address what is SMOT. And then you scale the data. Important. You scale it. You use scaling. You use SMOT to scale under certain nuances, certain conditions of the input data, right? And also, same case, you use hyperparameters and you fine-tune them using grid search. Mechanism. We'll address that tomorrow. But I'd like you guys to curiously figure out what are these and get some idea about them and build a logistic regression model. Pick up a solver, and then you've done that. You build the model, so your weight vector is built, and now you evaluate the model. And then you essentially evaluate for ROC, accuracy, confusion metrics, classification report, entire evaluation report, right? And then ROC curve and plot the curve, and also try to address and identify and plot the importance, weightage of each feature in the prediction, right? And then create the file that I had requested. Create the file with ID and the value, customer ID, whether interested or not for the test CSV, 1 or 0, right? So the output, there's no data, that has missing values, and so I'm using some C value 0.01 solver called Saga, and this is the confusion matrix. Oh, so doesn't look good, right? We want these negative this and this part to be what? What did we say confusion matrix, guys? We wanted the, let's see if I can, I think I don't have. So this part, we want this to be 0, and this part, this is false negative, and this is false positive. We want this to be 0, this to be 0, but there are sizable values here. So it looks like there are challenges with the model. So why and how to address them? So let's try to put some thinking tomorrow, but I'd like you guys to think through as well. This is the classification report. Again, we'll go through in deep tomorrow. This is ROC curve, right? Ideally, we want this here, 1, 1. This is what we want, an impulse, right? When true positive 1 always, and the false positive rate 1. So area under the curve we want to be 1, right? Recall curve, sensitivity, and then the feature importance, and of course you can generate a PV. Any questions, ladies and gentlemen? If no questions, I'll give a minute. If no questions, I know you must be hungry. No questions? All right, guys, thank you very much, and try to go through and put the code. Yes, Suresh, Professor Suresh.
Yeah, sir. Nothing. Yeah, thank you so much for the session, sir. So tomorrow, like around same timing, right, sir? 10:30 itself.
Yes, and let's try to get on time tomorrow. Students.
Sure, sir. Definitely.
Thank
Tomorrow,
you,
yeah,
Professor
we
Suresh.
can be on time. Thank you, sir. Thank you so much.
Thank you all, and have a good
Have a
Saturday.
nice day.
Bye bye. Stop recording.